and also my honor to come back to the school to give a talk. I graduated in 2004 and I did not come back after that, almost 10 years. So right now I'm at the University of Hong Kong, but currently I'm taking leave at UCLA for sabbatical. I work a lot with the industry, so the topic is on the power integrity and the signal integrity, which is two category technologies in the EMC. We are talking mainly we are trying to use CEM to solve them, but there are some sentences I want to cite. This was mentioned by Professor Todd Harbin this year in Florida when he was giving a tutorial at CES. He said this. He said CEM cannot solve EMC SIPI problems, but the EMC SIPI problem cannot be solved with CEM. So after I heard that, I found actually I quite agree with these points, and some of my activities actually resonate with this statement. So we are trying, because EMC SIPI problems are very complicated, it's very difficult to have a super artificial intelligence system that can solve everything. But CEM provides the power, provides the tools to overcome many physical problems, and then in terms of capability and capacity, therefore many problems that cannot be solved can be solved today. So I will go through a couple problems we solved. Some are very simple, some are not. This one is trying to use the rigorous Helmholtz decomposition to post-processing the solved solution for signal power integrity. Helmholtz decomposition is quite familiar for the CEM community. Also, it was popularly used for computational fluid dynamics. Basically, if you have a finite vector field, you can always decompose into divergence-free and curve-free field, and that's Helmholtz decomposition. And in EM at low frequency, we say that because the E and H field decoupled, and for the current, if I solve the current, you have the divergence-free current and the curve-free current. And in the solving, we use loop tree to solve it, but that is quasi-Helmholtz decomposition because the loop is divergence-free, but the tree is not divergence-free, and the tree is not unique. So this divergence Helmholtz decomposition we are using in CEM is not a true Helmholtz decomposition. It's a quasi version. So we are thinking if we can use a rigorous Helmholtz decomposition to really analyze the current or the field we got from the field solver. If we check, suppose we have vector field and we have divergence-free and curve-free field, then in the 3D case, you can rigorously derive that the divergence field and the curve-free field basically can be written in this way. And they are basically using the 3D static Green's function, even it is a dynamic field. And then this actually is not good because it means the divergence curve-free currents or field are populating all over the space. It cannot be really used. It's not physical. Then we have, if we care only about the surface 2D type of problem, then that could be used. And for the 2D type of problem for surface, then the decomposition can be written using this potential, the scalar potential, and the scalar potential can be written using the 2D static Green's function. In case you can get the divergence-free or curve-free, in case you can get the field. So to extract the field Helmholtz decomposition rigorously, we can follow this step. Suppose we got the field. It could be current or electric field, magnetic field. Suppose these are bases, and if the bases are R.G bases. And then we could get the divergence of this field, and use divergence of this field, and use the Green's function, the 2D Green's function, we can compute out the curve-free, the curve-free part of the field. And then from curve-free field or total field, we can get the divergence field. So why this is interesting, we can see some examples. The process is very simple, but its effect looks quite intriguing. First, we construct the artificial divergence-free field and curve-free field. This is a total field. And this is a curve-free field. This is a divergence-free field. Okay, they basically make sense. And we use a process, we can extract this and can verify the numerical process is correct. And then we apply it to the true problem. We have two coupled lines. Okay, then these two coupled lines, you will feed them using differential signal. Then we have the differential mode in this structure, and we can compute. You can using any tool. You use commercial tool or the tool you develop by yourself, and then you compute the current distribution on the ground plane. And this is the total current we computed on the ground plane. Okay, so the normal CEM tool normally in here you get the field, get current, then stop. You get the port information, then you give that to engineer, people begin to use it. But still, it's not enough. From here, we can use this rigorous Helmholtz decomposition process to get the divergence-free and the curve-free part. Okay, then this is divergence-free, this curve-free part. And then if we do not use this process, we just use conventional loop tree. We use the basis we use, then use loop current and the tree current. Then basically we cannot see any information from here. But if we use this rigorous Helmholtz decomposition, we can see here this divergence-free, basically you have this loop current corresponding to inductive coupling, and this you have the sources, and they basically propagating from one to the other, and this corresponding capacitive coupling. And if we use the common mode excitation, then this is the total current on the ground plane. And then for the divergence-free component and the curve-free component extracted, you can also see at this case, because these two currents go to the same direction, so your loop you have this loop right to the infinity. And here, your capacitive coupling is along the longitudinal direction. But if you again use conventional loop tree method, you cannot see any information from the decomposed field. And this can also be used for other, this is a complementary split ring resonator, and we pick different frequencies to check the curve rate, which is corresponding to capacitive region. So you have these gaps, they have strong capacitive coupling. And then for divergence-free, you have it corresponding to the inductive region, so normally around the loop structure. So this is a small problem that can be solved, but can provide some insight to the structure. Another work we try to do is try to do the hybrid simulation when we have EM parasitic problem together with the circuit problem, and try to use the DJTD method. And for the basic idea is we have parasitic system, have circuit system. We want to simulate them together. Then the circuit system will pose in different ways. You could have explicit circuit representation, or you could have some network parameter or measured data. Then how to integrate them into this EM system. Also, if I have nonlinear problem in the circuit parts, then how to integrate it with the linear parasitic system. So we use DG, which is the formulation started with here, and basically started with the Maxwell equation. Then we do the domain decomposition, and then for each element, each domain, you can expand them into bases, and then you can use the upwind flux to make sure that the continuity over the boundary. Then when we have the circuit, then the boundary between the EM part and the circuit will have the current, the circuit current that causes the jump of the field. So this part will actually get into the boundary condition of the EM. So when you formulate DG, you will have the current from the circuit that involve into the DG formulation. And this part has to be solved. It means we need to add extra equation that is based on the circuit. Then the circuit can be solved using KCL, KVL, and then the popular method that is kernel of space is the modified nodal analysis. So we can embed this modified nodal analysis into it, and in it we have the nonlinear capability if you have nonlinear components in the circuit. And then we need to couple the lumped network, circuit network with the EM parts. And the coupling process would be couple the EM to the circuit through a voltage source and the circuit to the EM part through a current source. And then you can integrate all the formulations together, and you can solve the hybrid EM and the circuit system. And this is for a linear problem, and we could solve. It has the supporting feeding system on the substrate together with a lumped small signal device model, and you can put them together. Then you can compare that with ADS. This is S21, this is S11. They basically agree with each other. Then if we have nonlinear MOSFET and has the bias system and put them together, you have nonlinear components in it. You can also do the simulation with the same method, same approach, and this is for the DC type of simulation. Then this is transient simulation, and then when you change the input signal power, then you shall see the harmonics, second and the third harmonics are spiking up quickly. So this agree with some references, including Professor Jin's references. Okay. And then the circuit part in the previous simulation requires explicit circuit model. But at many situations, you do not know that because the vendor does not want to disclose it. So we would like to do is, if we do not exactly know the circuit, but we know the network, okay? If we can get an admittance network of the circuit, then we can use the network to establish the relationship between the ports and connect that into the DJ's formulation. Still couple the admittance matrix system into the DJ simulation for the parasitic system. And with that, we can still do the hybrid simulation when you have an admittance matrix, not explicit circuit. Then third case is you have measured data instead of explicit admittance matrix. What will happen? Only measured data. Then if we have, say, S parameter is most popular measured data, then we can use it to S parameter convert it to admittance matrix, and then use the vector fitting method to fit it to get the admittance matrix. Then put admittance matrix into DJ, then to solve the problem. So this can be used to solve the practical problem. So this verification of how well this vector fitting process can be relied on to solve this problem. And then when you have EM circuit problem, you could have uncertainty. Your components could have certain changing range. Then how to consider that? So we can use we can add the uncertainty stochastic process into the DJ simulation, but if we change the kernel, it's very complicated. So one way is to do that, to do non-intrusive stochastic simulation. Very popular one is Monte Carlo, but it's very slow. So here we use a so-called adaptive sparse grid correlation method. It's much faster than the Monte Carlo simulation, but it can decouple from the solving kernel so that we can easily integrate the sampling point selection process together with the DJ simulation. And this is to solve this power amplifier problem, but we have several set of variations of the parameters in the circuit model. And then we can go to see how this circuit performance is being changed because of the uncertainty of the problem. Okay. And one last thing I want to talk, actually I added this morning on my way to here. Recently we tried to see for EMC, for SIPI, there are some problems like I have the coupling, the noise comes from point A to point B. And I want to know how this are coupled, and which part are contributing a lot to this coupling. And not only coupling, because the frequency is higher, how they radiate, how much this part is radiating, how much this coupling is contributing to the radiation. So when CEM solve problem, it solve everything, then give the numerical solution of every details. But how to analyze these details? So that is the purpose of this work. And we did that together with my former colleague at IBM, Al Rudi. He developed what's called the peak method. And we try to use peak method to analyze which part is contributing the power transfer, which part is contributing to the power radiation, and how much are they. So that was the purpose. I just skip it. So suppose I have two filaments, two metal filaments. Each filament has current on it. Suppose the power is injected into this metal filament. Then it has current, it induces current on this part, then it will radiate. Then this, because it induces current, it also radiates. And in between, they have transferred power. And these are the target we want to analyze, but at the same time, we can build the circuit model based on, basically it's an electric field integral equation. Build a circuit model, and this model is called a peak model, partial equivalent electrical circuit model. And this model, capacitive branch and has an inductive branch, and each one has a capacitive or inductive branch. There are several representations. Here we use control source, and these controlled sources are used to represent the coupling between different branches. And on this branch, which we call inductive branch, this control source is representing the coupling between inductances. And this are coupling between the capacitances. So with this, if we consider it's a dynamic problem, which is not a static problem, then we are going to have the so-called partial inductance and partial potential coefficient. And this partial inductance, partial potential will have a kernel as the free space Green's function, and that will be a complex. It means your inductance model and capacitance model will be complex. And this complex model will contribute to the coupled, to the controlled source in the inductive branch and the capacitive branch. And then use those complex voltage, complex inductance, and the complex capacitance. Then we can compute the radiated and transferred power from the inductive branch and from the capacitive branch. And then we can get the total radiated and transferred power. So it means at different pieces, you can explicitly analyze the coupling between them, the radiation of each of them, and also the radiation because of coupling between them. And if we use energy conservation to regulate all this relationship, because it's quite messy if you really put everything together, and if there are only two pieces, the total power shall be represented using this. And if we split them, you will have the Ohm loss, or the Ohm power consumed, which turns into Joule heating. And you have the self-radiated power, which is represented by these formulations. And you have the radiated power because of the coupling between them. And all the radiated power, if I have a two-body problem, A and B, the radiated power can actually be represented in the matrix system. And this can also be solved using the matrix system. And the transferred power can be calculated using, if the power injected into this part, then the transmitted power can actually be calculated using the Ohm loss and radiated power of this filament. And also it can be computed using the voltage, the induced source and the current on each branch. So when physical analysis, when we have this complex inductance, is if I have complex inductance, which is partial inductance, and its kernel is a dynamic Green's function, and if I assume it's low frequency due expansion, then this inductance is actually equivalent to a stereo of them, and this is the inductance, and this part for n equal to 1, 3, 4, 5, these are the resistance, and this part are the capacitance. And this can be done by multiply G omega, and then you can separate all these terms. And if you assume the low frequency, you can see that the inductance will dominate, and when frequency goes high, this thing will go high. So it's an inductive branch, and this actually is dominated by first term, so it's always a positive. And this, when frequency goes high, it reduces. So it's inductance curve. Then for capacitance, the complex capacitance also equivalent to a series of this. And a similar way, you can extend to get every component. This is obtained by divided by j omega. So with this, we can have a much better model and try to analyze different parts. Here is one example. We have the coupling dipole, and one is active, one is loaded. And we can get the radiated power of each and the total radiated power. And we also use the energy, we use the Ponting theorem to verify if we were doing the right work. And there are two resonant frequencies. And this is fundamental frequency, this is a harmonic. And we could say that they have higher radiated power, but the total radiated power is not exactly equal to the radiated power of the first single one, because you have the coupling. The coupling can be negative. The contribution of coupling radiated power could be negative, which means its radiation is destructive, is not constructive. And this is the transmission. The transmission means you have from A to B transmitted power, and this transmitted power will contribute totally to the radiation from the passive part and its ohm loss. Okay, so this agrees very well also. And this is another example when we have two transmission lines, and we could analyze the radiated power because it's a microstrip line, so radiated power is very weak, reasonable. And this transmitted power, it has like this standing wave pattern, which is also reasonable. We also use this method for other applications, including wireless power transfer, loop-loop coupling, and antenna problems. So we hope the paper can be published very soon. Right now it's in the minor revision. So I go back to this statement that the CEM cannot solve EMC problem, but EMC problem cannot be solved if there's no CEM help. Therefore, we are still continue working on this together with industry. This is one aspect we are working on. So that's the end of my talk. Thank you very much.